Hi, good afternoon. Sorry, good morning, everyone. Actually, we have habit of taking classes in afternoon, so it came out good afternoon. Anyway, good morning. So, how is everyone? I'm just waiting for one more minute for people to join, and after that, I will be starting with the session. So, just one more minute. Done. So, let's get started. I hope you all are good and fine. Hannah, done. So, in the very first class, I want to discuss first the strategy that we are going to follow in coming days to get prepared well for the coming exam. So, first of all, let's discuss like what will be the question pattern that you must be aware of. But still, I want to discuss about the level of questions that you're going to get in terms of it being easy, medium, or hard, right? So, 25% question that you're going to get will be your easy. Now the question is, easy means what? So in G mains, you have seen that EG means you're going to get questions directly from formulas. Done. Directly, you needed to put the formulas and get the answer. But here, 25% easy means putting the formula, getting the answer type not. Rather, here you will have to go for the application thing, simple application thing, like in G mains, if I consider, for example, like first 10 to 12 questions were like if you know the formula, you will be able to solve these questions. Done. And remaining questions were like if you know a little bit of application part of the formula, you will be able to solve all those questions as well. Done. So that left portion, the portion which is out of this 10 to 12 questions, that will come under easy portion of your G advance. That is your 25% easy, nearby. Done. Now, 45% questions that you're going to get will be of average level, that is moderate level, I must say. So that will be your moderate kind of. Now, what does one mean by moderate here? So basically, you will be able to solve this question only if you know the application part properly. Done. Means here you will need to do more calculation. Again, it won't be tough. You need to have a patience while reading these 45% questions. You need to be patient while applying the application part. You should not get anxious ki yaar, question is too big, how to read it, and I will have to do lots of calculations, so let's leave it. No, you don't have to do that. First, what you have to do, you have to read the question very carefully. It will be long, you have to keep the patience, and you have to read the question. Once reading part is done, you will get to know that the question is from the person I have already studied. And if I keep patience, if I keep faith on my calculation, I will be able to get it done. So for this portion, you have to be quite accurate with your calculation and also patient with application thing, right? So this 45%. Now, next remaining is your what? That is your 30%. And 30% questions will be your tough. Now, what will be our strategy? Definitely, our target is not to complete the 100% question. Nobody is going to do that. Even if somebody is going to do that, that's not our target. Done. So we are going to exclude completely this 30% tough questions. We don't have to touch it, right? We have to take care of this 71%. under which 25% will be easy, 45% will be moderate. And to solve this 70% questions, what is important is you must know all the topics, concepts properly, and its application part. It's not like G means that you know the formula, you will be getting things, right? Yes, knowing the formula is important because that is what used to be the first step actually, but that is not going to help you completely. You must know how to apply things. So the very first chapter that I'm going to start as a revision is your electrostatics and capacitance. So what I will be doing is I will be first taking you through concepts done in some 45 or 50 minutes. And after that, what I will be doing is we together will be solving questions. That is our strategy for the coming sessions. So let's get started. Okay, everyone, cool and calm. Dekho, one thing I want to mention again, you don't have to take any sort of tension then, because taking tension is after all not going to help you. What we have to do is in this 30 days, we have to stay with chapters. We have to patiently solve the questions. We have to read. We have to relax, and we have to feel like, yes, I'm going to do it. And even if not, I'm going to gain something. Done. So let's get it started. Done. So just give me 1 minute. Okay, so we are going to discuss first what first is your Coulomb's law, and in Coulomb's law we have already discussed all these things in Gmail, so I will be going quickly through this. So in Coulomb's law, what we do is we calculate force between 2 point charges kept at certain separation r. The limitation is it can only be used for point charges, and force value come as what k q1 q2 by r square here, where R is the separation between these two charges. What is K here? K value is your 1 upon 4 pi epsilon. Then epsilon is what? Epsilon is the permittivity of medium. Okay. So permittivity is what kind of thing? If you want to visualize permittivity physically, just imagine fog. So if there are two persons, suppose here there are two persons and they are standing before each other, and in between them there is a fog. So if fog is thicker, what will happen? They won't be able to see each other completely. Same is your permittivity. If permittivity is more, it means what? K will be less. And K less means what? Force will be less. So if permittivity is more, it means fog is more. Charges won't be able to see each other completely, so uh, they won't apply better force on each other. Then, so this is just like a fog. Now, what's the relation we need to remember here? Epsilon is equal to what? Epsilon r, epsilon naught. What is this? Epsilon equal to epsilon r, epsilon naught. Epsilon r is relative permittivity. Epsilon naught is what? This is your permittivity of vacuum. And what is the value if K is equal to 1 upon 4 pi epsilon naught? Then its value is equal to 9 into 10 to the power 9. Okay, with proper units. Okay, so these are the things you need to remember here. Now, what else we need to see ahead? Just okay. So here are the electric field lines. Lines you can see clearly here. So we already know for negative charge, electric field line will end, and for positive charge, electric field line will come out. So I don't need to discuss much here. Actually, I've just given the diagram. Here you can see one thing. One thing I want to say is as we move, like in the region where electric field is more crowded, if electric field is more crowded in a certain region, here you can see it is more crowded. Here it is less crowded. So in the region where electric field is more crowded, electric field intensity value is more, and where it is less crowded, its value is less. First thing. And second thing is electric field lines can't cross each other. Then if they cross at a point, there will be two different directions of electric field that can't be entertained. So that is not going to happen. Second thing, electric field lines can't be closed loop. Then it can't be like this because it can't start from single charge and end at single charge. Closed field lines means it is starting from the same charge and ending at the same charge. It is not possible, right? So such things I'm telling so that कि अगर आपका one like multiple choice question आता है, conceptual question आता है, you must know what is the reason behind electric field not being circular, right? Another reason is also that it's a conservative field. Now again it goes back to the same point, it can't start from the same point and end at the same point. Done. So it can't be circular in same. Now next, here you can see the electric field lines for a dipole that you already know actually. This is for two similar charges. Here the two similar charges positive, so definitely they will repel each other. And because of this repulsion, their electric field lines are also going away from each other. They are not, like if it is plus and it is minus, then electric field line will come from here and end at here. But since these two charges are positive, they will repel, and so their electric field lines will also repel each other. Done. So that is going to happen. Now, so force on positive charge, एक बहुत important चीज है that we need to remember here is force on a positive charge acts in the direction of electric field. You already know such things, but still it should be in mind while doing the calculation. There you don't need to go to the logic and try to find out, yeah, it will be true or false. You must be right in your head, force on positive charge acts in the direction of electric field. Electric field is more where E is crowded. E can't be circular in shape and also can't cross each other. So already we have covered all these things. Now there is a term null point. What do you mean by null point in electric field thing? So null point means the point at which your electric field is going to be zero. Then, so suppose you are having a two charge system. There is a plus Q charge, there is a minus Q charge, suppose, and we have to find the null point along line joining the two charges. So along the line joining the two charges, if we have to find the null point, first we will see if electric field direction is opposite in which space. Like null point we can get either in which regions. We can get that in this region or in this region or in this region. Done. So just draw the electric field lines first to find the null point position. Done. So plus Q के लिए electric field lines will go out like this. It will be like this. Done. It will be like this. And for negative charge, electric field line is going to be in which sense? For negative charge, it will be like this. Done. It will be like this. Like this, right? So you can see here, electric field line is opposite in this space and also in which space it is opposite. In this space, it is in the same direction. Just you see here, in the space between these two charges, electric field is in the same direction. So here, electric field can't be equal to zero because they will get added, right? And in this space, they are in opposite sense. There may be a null point depending on the magnitude of charge, or there may not be again. And in this space also, electric field lines are in the opposite sense. So there may be a null point or may not be depending on the magnitude of your charges. Okay? So just I wanted to tell you the concept of null point. If null point is coming in the question, it should take you to the sense that you have to calculate the point where electric field is zero. So electric field zero means their direction must be opposite and their magnitude must be. So first check for the direction of electric field, and that you can easily do by checking its the direction of its electric field individually. Okay? So that you have to do. Later we will do the question. So no need to worry about such things. Okay? Now Next is your electric flux. Electric flux you all must have studied. Again, this is a very important topic because here the application thing will come and so many questions come from this portion as well. So electric flux you already know. Suppose there is a rain happening. It is raining outside and there is no water in your room. You want to collect some water. You have a bowl in your hand. And what you are doing, you are keeping the bowl like this. So will you be able to hold some water in it? No. We need to change the orientation of this bowl, and how to change it, we can change it gradually like this. And if my bowl is like this, I will be getting the maximum amount of water stored. Okay. So how much water we are storing in this bowl will depend on how thick is the rain, and second, how I have kept the bowl, and what is the area of bowl. Done. So electric flux, you have studied already. Its formula is what? E dot ds. Done. So it depends on the intensity of electric field, that is intensity of rain, and it depends on the magnitude of area and also on the direction of area. Now the question is, what is the direction of area? What is area vector in short? So area vector is nothing but the direction that is normal to it. Suppose you have a square here, and suppose this is in XY plane. Done. So this plane I am calling as XY. So if this is in XY plane, area vector will be in where? In Z direction or in minus Z direction. So area vector will be either K or minus K. Done. So area vector is simply normal to the plane. Done. So this is your flux kind of thing. Done. Now let's go to the next portion. So here you can see the same thing. Just for the visualization, I have kept it here. Now electric flux through closed surface. We already know the formula of electric flux, right? Formula is what? E dot ds, yeah, E dot A, whatever you write, right? Now we are dealing with electric flux through closed surface. If the surface is closed, then what will be the value of electric flux through? So there is a formula for it. There is a separate formula, that is Gauss's law. But before that, let me show you. If the surface is closed, what first thing is what we mean by, what do we mean by closed surface? So closed surface means what? Closed surface means your 3D surface. Then whatever is 3D is a closed surface, like your cuboid, your cube, your cylinder, your cone, all these things are what? Closed surface. So this is a closed surface, 3D surface, right? Now, if closed surface is kept in a uniform electric field, here in the diagram, you can see the electric field is actually uniform. How we can identify by looking at the electric field diagram that it is uniform? In case of uniform electric field, spacing between two lines of electric field will be what? Constant. Then it will be what? Uniform electric field. Like here, if I am drawing something like this, and then this is not a uniform electric field because its spacing between lines are changed. So here the spacing is constant. So this is a uniform electric field. Now what's the flux through it? So the basic thing is if closed surface is in a uniform electric field, flux through it will be always zero. Then here you can see electric field line is entering this surface. Then how many number of lines are entering the first surface? Call it first surface. And it is exiting out of it. So call it second surface. You can see on first surface how many lines are entering? 1, 2, 3, 4, 5, 6, 7, 8. Some 8 lines are entering. And here also how many lines are exiting? Some 8 lines are exiting. So how many lines are remaining inside? Nothing. So the flux that is entering the cuboid is leaving the cube. So net flux through the cuboid is what? Zero. It is happening because the electric field is what? Uniform. Has it been not uniform, what would have been the case? Case would have been like, suppose 12 fields are entering and 10 fields are exiting. So definitely net electric field is some in terms of number of field line, it is 2, right? So if electric field is uniform and surface is closed, remember it is only true for the closed surface, then flux will be what? 0. Suppose I'm not taking a closed surface, I'm taking an open surface. Again, open surface means what? Open surface means your 2D surface. So here I can say first surface is an open surface, right? Second surface is an open surface. So if I have to calculate flux through the only one open surface, that is here, this one, suppose. So through this, net flux is there, right? Some amount of field is entering this surface, done. So flux through open surface will not be zero, but through closed surface, it will be what? Zero. Clear it? So this is all. If you have any doubt, you can let me know. You can text me here, or you can raise your hand. You can do everything you can want. I can unmute you. You can clear your doubt, because that is what keeps the importance, right? Now let's see what is the Gauss's law. So the statement of Gauss's law was for closed surface. So he said that for closed surface, amount of flux, that is total flux entering a closed surface, this is for summation, right, is equal to Q enclosed by epsilon. Now there are some important points that we need to learn from this expression. First thing is, what is Q enclosed, Q enclosed, and what is the significance of E here. And second, we will learn how to apply this in various questions, right? That is very important. So let me give you one example here. Suppose this is a closed surface. I'm saying this is a closed surface. I can't easily draw a 3D surface on a plane diagram. Okay. So let's assume this is a closed surface and there are various charge particles present like this and like this. So if my question is, what is total flux through this closed surface? So what I will see, total flux through the closed surface. So this is the total flux. Done. This is your what? This is your total flux. So total flux through the closed surface is equal to what? Charge enclosed inside the surface by epsilon naught. What is the charge enclosed? You see the closed surface. Inside closed surface, there are two charges present, Q4, Q5. And outside, three more charges are present, Q2, Q1, Q3. But in the formula, we can see it only takes Q enclosed. That is charges inside the closed surface. So charges inside the closed surface here is what? Q4 and Q5. So here Q enclosed will be equal to what? Q4 plus Q5 divided by epsilon. So this is going to be the answer here. Yani ki flux through the closed surface will be equal to this. Q2, Q1, Q4 are outside, so they are not going to contribute anything in flux passing through this closed surface, right? So this is the thing. Now, what is the significance of this electric field E? Now here you can see, suppose I am taking this point inside the closed surface. So at this point inside the closed surface, electric field will be because of this charge, because of this Q4 charge, because of this Q2 also, and because of this Q1 also, and because of this Q3 also. So electric field at any point inside this closed surface is going to be because of all the charges present in the space, whether it is inside or outside. So this electric field thing is because of all the charges present in the space, not only inside one, but overall this flux is because of only the charge that is included inside. Still, this again, this is a conceptual thing. You must remember this E stands for which charges, and this total E dot ds, summation of this E dot ds stands for which charge. Okay, so that is all I wanted to discuss in this section. Now let's see how we will be applying our Gauss's law. Okay, so how we are going to do that? You just see one thing here. E dot ds, what was our expression? Let's go there. Q enclosed by epsilon. Done. So finding Q enclosed is very easy. We will simply see how many charges are. We will simply see how many charges are there inside the closed surface. That will give us Q enclosed. But the problem here is how we will calculate this E dot ds. That's the question, right? So how we are going to do that? First, we are going to select the Gaussian surface. Okay? First, we are going to select the Gaussian surface. Again, this is the most trickiest part of applying Gauss's law. I mean, how we will select the Gaussian surface. That's most tricky, and that we should do more carefully. For example, what we are going to do while choosing surface, then so that I'm going to discuss now. So first thing is the Gaussian surface will be what? Your that Gaussian thing that you are going to take will be your 3D surface. First thing. Second thing, while selection, we will see that uh, like you just do one thing, you break this e dot ds. So if I'm going to break it, it will become e ds cos theta, integration sign. So under integration, we have three elements, e ds and cos theta. So if we have three variables inside integration, it is very difficult to solve, right? So somehow what we will try to do, we will try to reduce these three variables to one variable, right? So what we have to do that? So cos theta, somehow we will try to make this cos theta either equal to 0 or equal to 1. Yani ki either we are going to make theta equal to 90 or theta equal to 0 degree या 180. ठीक है? Like this we are going to deal with it. Now ds, leave ds. Suppose I am taking this as a variable. ठीक है? So again, e thing I will have to make this constant. So e we have to make constant. It means at every point on the Gaussian surface, we have to ensure that the electric field is constant. And if it is happening, E will come out of the integration sign. Cos theta value will become again constant. It will also come out. And only variable that will remain inside will be ds. Okay? So this is how we are going to choose the Gaussian surface. To an example, I will show you. And in some cases, you don't need to means you need to consider all these points while choosing in Gaussian surface, but there you will be calculating flux through individual surfaces. That I will again show you through the example, then only it will be clear. So let us do that first. ठीक है, चलो, किसी को डाउट हो तो प्लीज लेट मी नो. Again and again I am telling you. ठीक है. So what example we are going to take here is, suppose we have a line charge, infinitely long line charge. So here charges are distributed like this, and this is infinitely long. This is infinitely long. So what you have to do, whatever configuration is given, first you have to do is you have to draw the electric field lines. So if this is a positively charged, draw the electric field lines. So it will look like what? Since it is a positive, it will go out like this. And since it is an infinite, the electric field lines will be straight. If it is not infinite, if it is a finite, then what will happen? Electric field lines won't be straight. It will be something like this. Like this also it can be, because what is happening here now, since it is an infinite, again small things we need to learn here, because here the concept for advanced, your concept should be very much sound. Again here, why the electric field lines are straight, that we need to discuss. So chalo, I'm just showing you one thing. Suppose there is a positive charge element I am taking, and because of this I have drawn the electric field like this. Positively charged, so it is going out. Now what will happen, there is a positive charge element just up, and there is also a positive charge element just down. So these two elements will do what? It will repel this middle wala element, the middle element that you have taken here. This is also positive charge. See, so this positive charge will get repelled by this element and also by this element. So if it is getting repelled, it means its electric field lines will try to send this field line upward. It will repel, and this field and electric field of this element will also try to repel this field line, middle wale charge element ke field line ko. This will also try to repel. So this element will exert force on this field line in downward direction, and this element will exert force on this electric field line in upward direction. So downward upward force will get balanced, and it will make the electric field lines what? Straight. So for each element here, we can assume there is a element upward and there is an element downward. But if it is a finite, what will happen? For the corner elements, there won't be any element of charge in the upward direction. There won't be any element of charge in the downward direction. So for the corner, electric field lines will be curved. It won't be straight line, and that is called your fringe effect basically. In the capacitor also, you will study there is a fringe effect at the corner in the pattern of electric field. Why this is happening? It is happening because of this. Done. So it should be clear in your head. Now, what we were discussing? Yes. So we have to choose a Gaussian surface. So for choosing a Gaussian surface, first thing you have to do is you have to draw the electric field lines. We have already drawn the electric field lines. Now we have to choose a Gaussian surface in such a way that electric field lines should be what? Should be constant at each point of that surface. Done. So see what I'm going to do here. I'm going to select a Gaussian surface, which is a cylinder. Again, this is a 3D surface, so I can take cylinder. Why cylinder I have taken? You just see all the curved surface point of cylinder is lying at same distance from this wire, from this positively charged wire. So if it is at same distance, it means electric field value here is going to be constant. So throughout curved surface, electric field line is going to be what? Constant. So if we are going to calculate flux through the curved surface, for that electric field lines will be what? Constant. Again, check the angle thing. So here you can see here, area vector for the curved surface will be what? Area vector for the curved surface will be perpendicular, normal to the surface. So this can be the area vector, right? Electric field is also in the same direction. Done. So what we are getting here? We are getting here that area vector is parallel to the electric field. Yani ki theta is 0. Cos theta is also getting taken care of, right? And E is also becoming constant. So calculating flux here is quite easy. Now you just see here, flux calculation ke liye, we will consider 3 surfaces. One is curved surface, another one is this is top surface, and this is your bottom surface. Now come to this top and bottom surface. Here you can see area vector for this is what? This is area vector. And for this area vector will be what? This. Now see what will be flux through this. Flux is what? E dot A. So here area angle between electric field. Electric field is in this direction. Area vector is in this direction. Angle is 90 degrees. So flux through it is what? 0. Flux through this will also be what? 0. So if flux is 0, that is very easy. Flux is 0 through these two surfaces. And for curved surface, we can calculate flux very easily by applying the formula E dot ds. So you just see here, E is constant, ds into cos 0. Done. So E is constant, take it outside. Cos 0 is 1 ds. And this is equal to what? According to Gauss's law, Q enclosed by epsilon naught. Q enclosed by epsilon naught. Q enclosed by epsilon naught. Done. So flux through this curved surface is this, and flux through other two surfaces were what? 0. So total flux through this cylinder is what? 0 plus 0 plus this. And this will be equal to Q enclosed by epsilon naught. Now you can calculate it very easily, right? So E is constant, ds area of, integration of ds means total area. So total which area? Curved surface area we are talking about. So curved surface area formula is what? 2 pi RH, where H is the height of cylinder. So it is containing, suppose some L length of the wire. So height of this cylinder is what? L, right? So, and its radius, suppose we have to calculate the electric field at d distance. So its radius is d. Now you can write here 2 pi r is d here, and height is L here. So this will be equal to Q enclosed. Now we will have to see how much charge is inside. So how much charge is inside? So whatever charge is in the L length of wire, that charge is inside the cylinder. So suppose charge per unit length is lambda. So charge per unit length is lambda. So for L length, how much charge will be there? Lambda into L. So here you can write lambda into L. So L will got cancelled, and E equal to what? Lambda by 2 pi d. Okay, epsilon naught I have have left here. So lambda L by epsilon naught is here. 2 pi epsilon naught D. This is your electric field. So how you have to choose a Gaussian surface? First, you have to draw the electric field. And then you can either take a cylinder. For example, generally what Gaussian surface we use is cylinder, or we can take what? Cube. We can take what? Cuboid. You just see in each case, whatever question is there, first draw the electric field and check which surface, if you are taking, which closed surface you are taking as a Gaussian surface, like which closed surface you can choose as a Gaussian surface in that case. Done. So these three surfaces, closed surfaces, you keep in your head while solving question according to your Gauss's law. So what points you have to consider while choosing? You have to see that electric field should be constant throughout, or flux should be zero through other surfaces, right? Either it is zero or non-zero. If it is zero, question is solved. If it is non-zero, then we have to take care ki E is constant throughout and theta is either zero or 180 degree. Okay. So now this is done. Now let's see. So this thing we have already calculated. Done. Q enclosed we have already calculated. Now the question is of electric potential. We have already discussed electric potential. Again, concept is very important. Okay. So suppose there is a charge Q present here in this space. And what you have to do, there is a small charge plus Q at infinity. And you have to bring this charge to this P point. What you will do? Suppose you are just, suppose this plus Q charge is at rest. So its initial kinetic energy is zero. And you are releasing it from here. So what will happen? This plus Q charge will repel this plus Q charge and it will never come to this point P. Done. So if I have to bring it here, what I will do, I will apply a force on it in this direction. Done. And this plus Q charge will apply a force on it in this direction. Done. This is electric field force and this is my force. Done. Now suppose like when we are studying, wherever we have studied about this potential thing, we have taken a test charge, which is a very small charge. And again, we are bringing it in such a way that its acceleration is zero. Okay. So initially it is at rest. So finally also it will be at rest. It means I have to apply a force on it in such a way that net force acting on it is zero. So I will apply on it a force exactly opposite and equal to that of electric force. Done. So we are bringing it here, here, here. And during this process, I have done a work on it. And that work will basically bring it here. And in that process also, what is happening? Electric field is also doing work on it, exactly opposite to me. And that work will get stored in the form of its potential energy. And that is called what? Electric potential energy. Done. So if you're going to calculate work done by me, if I calculate work done by me, then it will be what? Fm dot dr. Okay. Fm will be equal to what? Fe. And its magnitude will be what? Kq by r square dr. Again, Fm dot dr, Fm dr cos theta. Theta is what? Zero. Kyunki I am applying force in this direction. Charge is also moving in this direction. So theta is equal to what? Theta is equal to zero. So cos zero I have taken as 1 already. So here if you're going to do that, Kq dr by r square, if you're going to solve it, what you're going to do, like let's put the limit from infinity to r. So you are going to get something like this. Done. Something like this you're going to get. So work done by me is this. Exactly opposite work will get done by the electric field. So work done by electric field will get stored at the potential, electric potential energy, and that will be equal to Kq by r. Okay, here. And if one charge is positive, another is negative, electric potential energy will be what? Minus Kq by r. Again, what is electric potential? That is work done per unit charge. So here work done per unit charge, if you're going to calculate this will be this. Why I explain this thing? Just to make your concept clear. Because again, while solving advanced question, you don't need the formula directly. You need to know from where the formula is coming. That is very important. So you need to stay with each and everything, right? So that is why I explained it here. And this is your potential. Done. Done. I'm not simply uh, doing the calculation. I'm doing because I want you to understand from where it is coming. Now from potential thing, like you already have done in your G mains kind of thing, if you have to bring charge from infinity to here, how much work you will be doing. So you already know such kind of, right? So I'm not going to deal with this. Again, one important thing I want to discuss here. Just say in the previous case, I saw that there was a charge plus Q, and under the influence of this plus Q charge, I was bringing a charge Q from infinity. Okay, that thing we did. And also here you must have seen that if we are bringing a Q charge from infinity to this point, suppose here we are bringing, so we are not doing any kind of work. Why? Because in this region there is no electric field, there is no external charges present. But if we are bringing another Q charge here, then we will have to do work on bringing this charge because there is a charge Q already present in its vicinity. Done. So that work done is taken as KQ by R. Done. And if here it is coming another charge, then on this work will get done because of this charge also and this charge. Done. Now, a different thing I'm going to tell is कि यहाँ पे suppose कर लो there is an external electric field present already, and I have two charges at infinity, Q1 and Q2. So I have to bring Q1 at certain point, suppose at point this P. So how much work I will have to do? Again, when I was bringing Q here first time, no work was getting done because no external electric field or external charge was present. But here external electric field is present. And because of this external electric field, in this space, at every point, there will be certain potential value. Done. So suppose here the potential is V1. So how much work I will be doing in bringing Q1 from infinity to here? Work done per unit charge is defined as what? पोटेंशियल या पोटेंशियल डिफरेंस आप बोलोगे, क्योंकि हम लोग इंफिनिटी पे पोटेंशियल को क्या मानते हैं? जीरो. इसलिए जब भी कोई चीज को लाइक व्हेनेवर वी आर ब्रिंगिंग एनी चार्ज फ्रॉम इंफिनिटी टू सम पॉइंट, वी टेक पोटेंशियल डिफरेंस एट v, क्योंकि एट इंफिनिटी वी हैव टेकन पोटेंशियल टू बी जीरो. So work done per unit charge is either potential if we are bringing charge from infinity to certain point, or it is equal to potential difference. We can quote it like this, right? So here work done will be what? Q1 V first. Now, when we are bringing second charge to suppose this point Q, then what will happen? This Q point has suppose potential V2. So on this Q2 charge, work will get done by two things. First is external electric field, and second thing is Q1 charge already present here. Done. So work done by electric field will be what? On Q2, Q2V, and work done by this Q1 charge will be equal to what? That because of two charge system. Okay, this way. So if we are bringing two charges or three charges from infinity to certain region where electric field is already present, then work done by electric field will also get added. This thing you have to keep in your mind. You don't have to escape it. That is why I mentioned it here. Okay. Sure. So next is what? Next is your relation between E and B. We already have studied this relation also. So dV equal to what? Again, potential is a scalar quantity. So dV equal to, dV is dot product of two vector E and dr. E is electric field, dr is position vector. So minus E dr cos theta. What is significance actually? So its significance, very important significance is that you just see dV will be minimum. Minimum, why I'm saying? Because here there is a negative sign. So dV is going to be minimum when E will be max, dr will be max, and theta will be max. So suppose E and dr are fixed. So E dr cos theta will be maximum when cos theta is maximum. And cos theta will be maximum when cos theta is maximum when theta is equal to what? 0 degree. Cos theta is minimum when theta equal to 180 degree. Okay. So here we have to maximize this value to minimize dV. Done. So minimum value is EDR when theta equal to what? 0. Again, theta 0 का मतलब क्या हुआ? Theta 0 means angle between electric field and DR. This theta is 0. It means E and DR are parallel. Again, what is the meaning of this? It means if we are moving in the direction of electric field, if we are moving in the direction of electric field, if our displacement, our position vector is in the direction of electric field, then potential will decrease the maximum. So if it is shown that here potential is 10 volt and here it is 5 volt, here it is 1 volt or 0 volt you say. So potential is decreasing sharply in this direction. Done. And also one another thing is given. Here it is 10, here it is 8, and here it is suppose 6, here it is 4, something like that. So in this direction potential is also decreasing. In this direction potential is also decreasing. But in this direction potential is decreasing more sharply from 10 to 5, 5 to 0. Here 10 to 8, 8 to 6. So less sharply. So electric field direction will be in which direction? It will be in this direction. Because electric field is used to be in the direction in which potential decreases the maximum. That is what we discussed here. So whatever I discussed, its conclusion was that the direction in which potential decreases the maximum, electric field used to be in that direction. That was simple. That was my motto actually. So in the direction of electric field, potential decreases the maximum. Now, what else we need to learn here? There is a term potential gradient. You must have studied here. So here you can see dV equal to what I can write here. dV equal to E minus E dr if theta equal to 0 degree. I'm taking theta as 0 degree, suppose. So electric field can be written as dV by dr. Okay, it can be written as dV by dr. Now, suppose potential is written something like x square y cube z, something like that, and you have to calculate its electric field. So how you will do that? Potential is as a function of x, y, z both. It means we are moving in a direction where x is changing, y is changing, z is changing, right? So here dr can be written as dx I cap plus dy j cap plus dz k cap. Something like this we can write. Again, I'm just simplifying the thing. I'm not properly writing the sequence because I just need to give you the vague idea of how to use it, right? So what you will do here, t v को आप लिखोगे whatever it is given x square y cube z. So first you will differentiate with respect to x. This will become I cap plus d. Again value of v you will put and dy cap plus again the value of v you will put and dj. Yani ki when you are differentiating it with respect to x, you will consider yqz as constant. So it will come out, yqz will come out and differentiation of x square will be 2x. So the value of this we are going to get as what? It will become yqz constant, bahar le liya, x square ka differentiation, that is your 2x. So this thing we are going to get. Similarly, we will do the rest. So this is your basically the way to calculate electric field if voltage is given in terms of x, y, z. Done. Clear? So this is your E dot. E dot dr. I have just taken here theta equal to 0 just for making you just for making things more simpler and simpler. That was not required if I had followed all the sequences. Okay. But the main thing is ki you have to go in this. Okay. Chalo. Next, we need to move ahead. Yeah, this is a very important portion actually. So this is your conductor in an electric field. So what happens when we are keeping conductor in an electric field? Done. Oh my God. Done. So what's happening here? Suppose there is an electric field and there is a conductor kept here. Here I have taken a conductor. So by conductor, what do you mean? Conductor means it has so many free charges. So it has so many free charges. Suppose plus minus, plus minus. Just to make this thing simpler, I'm taking plus minus like this. Okay. So they have so many free charges, electron and proton kind of ions, anything you can consider. So these are randoms. Done. So at room temperature, this conductor is kept. Now what will happen at room temperature? You have studied in thermodynamics. T at T temperature, it will have some energy, and because of this energy, it will be random. Now what is happening? I'm keeping this conductor inside electric field. So if I'm keeping this conductor inside electric field, what is going to happen? First thing, what we are going to get, so it has so many electrons and positive charges, electrons, positive charges like this, so many, done, all random. Now, if we are keeping it in an electric field, what will happen? Just now we have said that the electric field applies a force on positive charge in its own direction, and on negative charge, electric field will apply force in the opposite direction, right? So positive charge on positive charge, force will act in the direction of electric field. So this positive charge will start accumulating on the right surface, and negative charge will start accumulating on the left surface, right? So because of this accumulation, what will happen? Electric field will get generated inside, and this generated electric field will be in opposite sense to that of external, right? So this is your E induced, and this was your E naught, yeah, E external, call it E external. This is E induced. Now what will happen? Because of induced charge, sorry, because of induced electric field, which is in opposite sense, force on positive charge will act on the in the opposite direction. So because of induced electric field, what is going to happen? If I explain it here, induced electric field is in this sense, done, and external electric field is in this sense. So if there is a free charge inside conductor, this uh, free charge, suppose this free charge is positive, so on this positive free charge, external field will apply force in this direction, and induced electric field will apply force in this direction. And if these two electric field becomes equal, then this net force will become zero, and no more charges will accumulate on the surface. So in conductor, what happens? Charge will, because of external field, positive charge will first go on right surface, negative charge will go on left surface. Because of this charge accumulation, induced electric field will be there, and because of this induced electric field, force will now act in the opposite sense to that of initial one, because of to that of force because of external field, done. And this opposite force will gradually balance the external force, and at that point no more charges will accumulate, and that is called equilibrium has reached, done. So at equilibrium, no net accumulation of charge will happen on the surface of conductors. I'm saying no net. Again, remember, I'm saying no net. It doesn't mean charges are not going here, not going here. It may happen, but net accumulation of charge will be what? Zero. Done. So from here, questions have been asked actually. Once it was said that inside conductor, electric field will be always zero. No. Inside conductor, electric field will be zero. Looking here, what is happening? Uh, Net force is getting zero. It is only possible if induced electric field is equal to uh, external electric field. So inside conductor, electric field is finally becoming zero. But before that final time, what was happening? There was a phase where external electric field was stronger than induced electric field. So actually, not always electric field is zero inside a conductor. For some fraction of second, for some microsecond, what is happening? There is a certain electric field inside the conductor. So if question is asked like, I'm dropping a conductor, I'm dropping a conductor in an external electric field. So at t equal to 0, between t equal to 0 and t equal to 10 to the power minus 9 second, electric field will be 0 or not. So it may not be 0 or it will not be 0 because it takes some microsecond to get assembled like this. Yani ki for some fraction of second, what will happen? Electric field will not be 0. But for significant time, if we are talking for millisecond or for some second, then definitely electric field inside conductor is what? 0. So electric field inside conductor will be what? 0. If we are neglecting that fraction of second, right? So that is important that you should keep in your mind while you're doing the question. Now, uh, we have already done this. So E inside conductor is 0. Now, what is the significance of this? That we need to learn. So just now we have studied electric field inside a conductor is what? 0. So suppose Karlo, what I am doing, this is a conductor, suppose. Done. So this is a conductor. This is suppose a metallic solid sphere. This is a metallic solid sphere. And what I'm doing, I'm giving it certain amount of charge. Done. So if I'm giving it certain amount of charge, what will happen to this charge? This is the question. Now, if you remember Gauss's law, we have studied in Gauss's law that E dot ds equal to Q enclosed by epsilon. Done. So if you consider here, I have just now told you that if we are neglecting the fraction of second, that we neglect unless and until it is not talking about that fraction of second. So then we say that electric field inside conductor is what? 0. So here electric field inside conductor will be 0. So suppose what I'm doing, I'm taking a point inside a conductor here and I'm trying to calculate electric field. So this point is inside the conductor, here electric field will be what? 0. So electric field is 0. Now what I'm doing, I am trying to calculate flux through the closed surface passing through this point. Done. So what will happen? Inside this closed sphere also, at everywhere electric field will be what? 0, because this is inside the conductor. What will be the flux? So if E is 0 everywhere, flux is going to be what? 0. Done. So if flux is going to be 0, what we will have to do? Q enclosed bhi kya hona chahiye? 0. So if I am giving it some Q charge to a metallic sphere, and if suppose it is getting evenly distributed inside the solid sphere, then what will happen? There will be certain amount of charge inside this closed surface. But inside this closed surface flux is what? 0. So Q enclosed should be what? 0. This is only possible if whatever charge I'm giving to it, that will go on to surface. Done. So it will go on to surface. Done. Then only this will be 0. Done. So whatever charges we are giving to a conductor, that will go on to surface. First thing. Second thing, how it will get distributed on the surface. So if here I have taken a metallic conductor, metallic solid sphere, right? So it has a radius r. So this every point on this sphere is part of a solid sphere whose radius is r. Yani ki its curvature is constant throughout. Every point has a radius of what? Every curvature, if you are taking, it has a radius of what? R. Done. So radius is same. So if radius is same and you are giving it a charge Q, then all this charge will go on the surface and it will get evenly distributed, uniformly distributed, right? So it will get uniformly distributed and our electric field will look something like this. Again, I will come back to this, how electric field will look like, but it will get uniformly distributed. Now the question is, if I am taking a closed surface like this, how my charge, if I'm giving it a charge Q, how my charge will get distributed? Where the charge will be more denser and where the charge will be more rarer. So already I have discussed this thing in G mains. I have discussed that if there are two conductors, one is having charge Q1 and another is having charge Q2, and they're getting connected by a wire, then what will happen? Initially, there was no connection point actually. Okay? Initially, this connection was broken. So it was having a charge Q1, it was having potential V1. kq1 by r1. It was having potential kq2 by r. v1 v2 के बराबर नहीं था, but once we are making the connection, what will happen? Charge will flow from high potential to low potential until potential of both the sphere will become constant. So I have already discussed such thing. So you will see that potential, sorry, not potential. So here you will see that final charge distribution on two surfaces will be directly proportional to their radius, but charge density, that is surface charge density on two surfaces finally will be inversely proportional to your radius. Done. It means the one which is more curved, will get what? Like sigma 1 dash is what? Inversely proportional to its radius, right? So Q is directly proportional to radius. If radius is more, Q will be more. And sigma is inversely proportional to radius. It means if radius is more, sigma will be less. If radius is less, sigma will be more. Now, suppose I'm giving you an example here. Suppose I have a conductor like this. Okay? And I am giving it a charge Q. What will happen? Which surface has the highest, more radius? This is a straight one, this has radius of infinity. So here very small amount of charge will come. This is a curved, more curved. So it will have more charge than that of what? This straight one. Now just focus on this small region. This is small region. It is very much curved, right? So here large amount of charge will accumulate. Why? Because just now I have told you that sigma is inversely proportional to radius. If radius is less, sigma will be more. So if we are giving a charge to a conductor, it will go onto the surface, and on surface, how it will get distributed will depend on what is the radius of curvature of the surface. That is for sure. Okay? Done. Now there is one more significance of it. Just now I have shown you that how charge, if we are giving charge, what will happen to that, and how it will get distributed. Now the next thing is, if electric field inside conductor is 0, there is one more significance to it. Suppose we have studied one more formula, E dot dr. Yeah, dr, whatever you write, dv equal to E dot dr. So if to a conductor we are giving charge, what is happening? Inside conductor, electric field is 0. All the charges is going on the surface. Done. Inside electric field is what? 0. So if electric field is 0, this dv will become what? 0. So if dv is 0, v will become what? Constant. So if v is constant, it means what? Potential inside conductor will be constant at every point. And that constant value, suppose this is a conductor and this is 0.1, 0.2, this is 0.3. So at 0.1, 0.2, 0.3 potential will be same. And this same value potential will be same as that on the surface. So if 0.4 I'm taking on the surface, potential V1, V4, V2, V3 all are equal. What is significance of it? Again, it has two significance. One significance is with work done. Suppose you have to take a charge from 1 to 2. So Q1 charge from 1 to 2. Since potential of 1 and 2 is same, potential difference is 0, work done will be 0. Because work done per unit charge is written as potential difference. Done. So work done is 0. Now, it has also one significance, that is what will be the direction of how we will draw the direction of electric field for conductor. Suppose in this case, I'm giving it a charge Q, and definitely it will go on the surface. You know, that you already know. So it is going on the surface. Now what is happening? I have to draw the electric field. So how I will draw the electric field? So electric field, suppose I have drawn like this. Is it true? It is not true. Why? Suppose like this. So this point take as 1 and this point take as 2. So suppose I have to transfer a charge, move a charge from Q from 1 to 2. So electric field is in this direction. This angle is theta. So E cos theta will be the component of electric field along the surface. So along the surface, there is an electric field. And if there is an electric field, this will apply a force on the charge moving on the surface. So if charge is moving along the surface, electric field is along the surface, force will act on the charge and it is moving from one point to another point. There is a displacement, so there will be a work done. So work done not equal to zero दिख रहा है अगर electric field ऐसा लेते हैं, done. But we have already discussed that work done will be zero because potential throughout will be same as that on the surface, done. So work done can't be non-zero. It means electric field can't be like this. Electric field will always be perpendicular to the surface of conductor. If you are drawing an electric field for conductor, it will be always perpendicular to the surface. It can't have a component along the surface. That is why. So this is wrong, and this is also wrong. Done. So these are the ways we will be keeping in our mind while doing the calculations. ठीक है? चलो. So now, hole, we will just move through certain kind of thing. I have already discussed such things. So now let's see. Here you can see electric field means this diagram represent there was an electric field. Done. There was an electric field like this. And what happened? I kept the metallic conductor here. So what will happen? This electric field line will not stay straight any longer. Why? Because once I will drop the conductor here, on positive charge, force will act in the direction of electric field. So it will get accumulated on the right surface. Negative charge will get accumulated on the left surface. And electric field on the conductor can't be anything but normal to the surface. Done. So we will, so electric field will get rearranged in such a way that it is always normal to the surface. Yani ki always directed towards the center, always normal to the surface. That is why this electric field lines is getting molded like this. Okay, so these are the things you need to keep in your head while you are looking at the diagram and if questions come from such portion. Okay, again here you can see just now I have discussed the configuration part. Here you can see this conductor is having different curvatures. Each curvature has different radius, and the one which has higher radius has got lesser density charges. Just like here you can see here positive charge less, here negative charge less, and this region has the highest curvature. So here positive charge is crowded. Here also negative charge. Why negative positive? Because this was a neutral conductor kept in an electric field. Positive charge will get accumulated towards the right and negative charge towards the left. But they won't get evenly distributed because of the different curvature of the conductor. Okay? So these are the things you need to keep in your head. Again, more diagram I have included just to show you more things. Again, here the same curvature wala thing is coming into account. Here you can see again, this is a positive charge, and because of this external positive charge, electric field is existing in the region, and in this region some conductors has been kept. So let's focus on this conductor. What will happen? This electric field, because of this electric field, first thing you have to see that inside conductor there will be no electric field. So through the conductor no electric field is passing. Again, how charge distribution will happen? In the direction of electric field, positive charge will get accumulated. In the direction opposite to the direction of electric field, negative charge. Already we have discussed. Again, at corner you can see at corner more charge accumulations are there. More charge density is there. Why? Because its radius is almost equal to 0. Similarly, you can see here. Done. So these diagrams should make you more clear about how charge will get distributed. Again, this is one important thing that I want to discuss here is you just see here what is the case. There is a conductor. This is a solid sphere, metallic solid sphere. A cavity is made inside. And what is happening? Suppose at the center of cavity, just see this thing very carefully. At the center of cavity, I'm keeping a charge Q. So this is a cavity. This is not a conductor. Done. Cavity means air hai, open space hai. Done. So in open space, electric field can exist. Inside conductor, electric field can't exist. So how the charge will get distributed? We have to see here. What I mean to discuss now. My point is that you are given a conducting a solid sphere. And what is happening? There is a hole inside, that is cavity. And at the center of cavity, a charge Q is placed, suppose. And you are asked to draw the electric field lines. How you will draw? Simple. So, सबसे पहली चीज that you are going to do is, because of point positive charge, electric field will be like this. है ना? Like this. Now, this is a cavity, but this region is a conductor. And we have learned already that inside conductor, electric field can't be zero. Sorry, electric field can't be non-zero. Sorry. So here the electric field will be what? Zero. It means no electric field lines will be in this space. So we don't have to draw. Again, here you can see this is the air. So here electric field will be there because of this charge. So again, we have to draw like this. Done. Done. So be wise in drawing things actually, rather than getting confused by things. Ab dekho, I have drawn electric field like this. Because of this configuration, I can now easily draw the charges. There was a positive charge. Now you can see here electric field lines are ending here. And it's again emanating from here, releasing from here. Electric field line can only end if negative charge is present. It means this positive charge will do what? It will attract all the negative charge of this conductor on this surface. Okay? And if negative charge is getting attracted here, positive charge will stay on this surface. So it is like this. Okay? So this way the configuration is happening. Now here what difference is coming is we have not kept the charge at center of cavity. We have kept it somewhere else. So because of keeping it somewhere else, what difference is going to come? That now I am going to discuss. So suppose there is a cavity and there is a solid metallic solid sphere, and center is this. I'm keeping charge here, Q charge here. So definitely in this point is more closer to the charge rather than this point. So at this point, electric field will be less. At this point, electric field will be more. So here the electric field lines will be more crowded. And here the electric field lines will be less crowded. So this is for sure done. So that is why electric field lines are looking like this. Again, you have to draw it normal to the surface, remember, okay? Because this is a conductor. Now this is more crowded here and this is less crowded. So here more negative charges like this, and here less negative charges like this I have drawn, right? Now positive charge will get distributed on the outer surface. Just now I have discussed. Now the question is, if negative charges is more concentrated here, it means does positive charge will also be more concentrated in this region, in this surface? No, it won't happen. Kyuki there is more negative charges here present, more denser negative charges are here, will not get communicated to the outer surface because this electric field line is not crossing this region and reaching here. Had it crossed, it would have communicated, but it is not crossing, no communication. So whatever charge is kept at center or at this place, at this place, at this place, that communication is not happening to the outer surface. Outer surface doesn't know anything about the placement of charge inside the cavity. Done. Clear hai? So again on the outer surface, charge will get only uniformly distributed. This is very, very important. Okay? This you need to remember. Okay? Done. Why this is happening? Because this electric field is not able to cross the region because there is a conducting region. So no communication is happening. That is why uniform. Done. Chalo, theek hai. So again here, no induced charge on the surface. Why? Because you can see here, positive charge I have given to the cavity, same amount of negative charge we have given to the another cavity. So total charge inside the cavity or inside the conductor is how much? 0. Total charge inside the conductor is 0. So on the surface also, no charge will go. Because to conductor, whatever charges we are giving to the conductor, that amount of charge will go on the surface. If net charge given to the conductor or to the cavity is 0, it means no net amount of charge will appear on the surface. Okay? So that's simple logic. Now these are just the formula that I have already discussed before. So I'm just going to take you through the things. So this is a formula for conducting, non-conducting. Uh, एक second. So the formula for conducting, non-conducting hollow sphere या conducting solid sphere, तीनों के लिए ही क्या होगा? सेम होगा, whether be it for electric field or potential. क्यों सेम होगा? क्योंकि if you are taking conducting hollow sphere, again this is a conducting hollow sphere, this region is hollow cavity, so whatever charges you are giving, that will stay on the surface, है ना? And if it is a non-conducting hollow sphere, again charges will stay on the surface only, because inside it can't, no, it is hollow. And if you're taking conducting solid sphere, this is a conducting solid sphere, even if we are giving it a charge, inside there is no cavity, this is a solid region, but still charge will not stay inside because this is a conductor, it will appear on the surface. So it will behave like inside there is no space to keep the charge and charges are on the surface. So by geometry, conducting, non-conducting hollow sphere and conducting solid spheres are the same. So for them, formula will be same. Potential inside, yeah, on the surface will be equal to what? KQ by R. Potential will be this. Electric field will be inside, or inside will be electric field value inside will be what? 0, because there is no charge inside. And electric field on the surface will be equal to what? It will be equal to KQ by R square. Done. Clear hai? Electric field outside the sphere will be how much? KQ by R square. And potential outside will be how much? KQ by R. So these are the formula you already know, right? I just kept it for the revision. Now let's move on to the next. That is also just the revision wala thing that we have discussed. So I have just kept the formula. Electric field R less than R के लिए क्या लिखोगे आप? R less than R, rho R by 3 epsilon naught. Again, I am giving you here a homework. You should calculate it using Gauss's law. Please derive it. I want you to derive it for the clarity. क्योंकि क्या है ना, you are going to deal with a G advanced question, and here you should know how things are coming. Done. So derivation of this you have to try, not you have to do it, and this also derivation you have to do it as a homework. ठीक है, rest things are clear, we have already discussed. ठीक है, so we don't need to do now. Without wasting any time, conducting seat. Again, here one important thing I want to discuss. What is the difference between conducting and non-conducting seat? Okay. So if there is a conducting seat and you are giving it a charge Q, what will happen? Since this is a conductor, what will happen? Suppose this is a phone and this is a conducting phone. So if I'm giving charge to this surface, that charge will also travel to this surface, right? So conductor means it will conduct. If you're giving it a charge here, it will get distributed here. So conducting seat means charges distribution will be on the both surfaces. Okay. So this is the basic meaning of conducting seat. And what is the meaning of non-conducting seat? If I have to make it a non-conducting seat, what will I have to do? There will be no electric field in this sense. Why? Because if the seat is non-conducting, it means if I'm giving it charge to this surface, that charge will stay on this surface only. No charge will travel on this surface. So from here, no electric field will come out. Only from first surface, electric field will come out. So electric field will only be in this place. Okay. So formula for conducting and non-conducting is what? So electric field at any point before the non-conducting seed, it is sigma by 2 epsilon naught. And for conducting seed, it is how much? Sigma by epsilon. This you need to remember, nothing else. Okay? Chalo. Now, dipole thing you have already studied, right? Dipole you already know now. Dipole is what? Negative and positive charge separated by a certain distance. And here this distance is how much? This is equal to 2a. So dipole value we used to write T2q into a. Q into 2a. Right? Its direction will be from minus q to plus q. This is called axial point and this is called what? Equatorial point. At axial point, electric field used to be equal to what? 2 kp divided by rq, and its direction used to be in the direction of dipole. And here electric field used to be what? Kp by rq, and its direction used to be opposite to the direction of dipole. So this was the simple formula we have studied before as well. Now suppose we are given a dipole like this, and we have to what? We have to find the electric field not at axial point, not at equatorial point, but at any other point. How we will do that? So the simple logic is what? Suppose at theta angle I have to calculate. Okay? This distance again given is what? 2a. So here we have to calculate the dipole. What we can do, electric field value. What we can do here is, you can simply see here, dipole moment is in this direction, and I have to calculate electric field at this point. So you can see here clearly, we can break dipole into two directions. In this direction, dipole moment is P cos theta. And in this direction, dipole moment is how much? P sin theta. So now consider question like this. Consider question like you have to calculate electric field at this point because of two dipole. One is P cos theta in the direction of, in this direction only, and one is P sin theta in this direction. So for P cos theta, this is an axial point, and for P sin theta, this is a equatorial point. You can see that clearly. So P sin theta ka axis I am drawing like this. Done. So for this point is a what? Equatorial point, and at this point, electric field will be opposite to its direction. How much? Kp sin theta by rq. If this distance is what? R. Now, for P sin theta, if this distance was R, and for P cos theta, this is an axial point. Done. And for axial point, electric field used to be in the same direction as that of dipole. So it will be in this direction. What will be the value? This value is this much, and this value will become 2 kp cos theta by rq. Now these two are at 90 degree. Net electric field will be in this direction. You can calculate it back, right? So this was the logic. Done. Now, what if we are keeping dipole in an external electric field? So we have already discussed in our advanced classes that when we keep dipole in an electric field, what happens? If the electric field is uniform, that you can see here, it is uniform because distance between two lines is constant. So if electric field is uniform, force acting on positive charge here will be how much? It will be QE, and on this force will act in this direction, opposite to the electric field, it is negative. Magnitude of these two forces will be equal. Since electric field is uniform, net force is going to be what? Equal. So net force is going to be 0. So net force acting on dipole will be 0 if dipole is kept in an uniform electric field. If dipole is kept in non-uniform electric field, net force will be what? Non-zero. Okay. What will be the torque acting here? So torque acting here will be what? We have already learned the formula P cross C, P sin theta. And since this is a two charge system kept in an electric field, it will have certain kind of potential energy, and that potential energy here is written in the form of minus P dot E. So these are the formula that we have already studied. Now, equilibrium of dipole that I wanted to discuss a bit. So equilibrium of anything means what? Equilibrium means two type of equilibrium will be there. One is your what? Translation wala equilibrium. Translation translational equilibrium, and another is what? Rotational equilibrium. ठीक है. Translational equilibrium कब होता है? We already have studied in our mechanics when net force acting on the body is zero, and rotational कब होता है? जब torque zero. तो डाइपोल के केस में आप देख लो, ट्रांसलेशनल इक्विलिब्रियम में डाइपोल कब होगा? जब उस पे नेट फोर्स जीरो लगेगा. नेट फोर्स जीरो कब लगेगा? जब मेरा इलेक्ट्रिक फील्ड क्या होगा? यूनिफॉर्म होगा. नाउ रोटेशनल इक्विलिब्रियम में कब होगा? जब उस पे टॉर्क जीरो लगेगा. टॉर्क जीरो कब होगा? टॉर्क का वैल्यू हमने क्या देखा? P sin थीटा. ये जीरो कब होगा? ये जीरो दो केसेस में होगा. आइदर थीटा जीरो होना चाहिए या थीटा क्या होना चाहिए? 180. In that case, it will be in what? It will be in rotational equilibrium. So this is the case of rotational equilibrium, right? So the dipole will be in total equilibrium, in complete equilibrium, only if electric field is uniform and angle between dipole and electric field at either 0 degree or 180 degree. So here two angle cases are coming. Now we will discuss two kind of things. One will be your what? One will be your stable equilibrium and another will be your what? Unstable equilibrium. ठीक है. तो चलो अब देखते हैं. दो तरह का इक्विलिब्रियम हमें देखना है. डन. सो टोटल इक्विलिब्रियम, यानी कि टोटल इक्विलिब्रियम कहने का मतलब कि एक्चुअली इक्विलिब्रियम ये कब हुआ हमारा? ये कब हुआ? जब हमारा इलेक्ट्रिक फील्ड क्या हुआ? यूनिफॉर्म हुआ, या मेरा थीटा क्या हुआ? जीरो, या थीटा क्या हुआ? 180. इन दोनों में से एक. तो मुझे टोटल इक्विलिब्रियम. अब ये टोटल इक्विलिब्रियम दो तरह का होगा. एक स्टेबल होगा और दूसरा क्या होगा? अनस्टेबल. ठीक है. स्टेबल कब होगा? देखो कोई भी चीज स्टेबल कब होता है? एनीथिंग यूज्ड टू बी मोर स्टेबल इफ इट एनर्जी इज लेस, and anything that has more energy will be unstable. Suppose you have very high energy, you won't sit at one place, you will just roam around, you will go from one place to another, you will be anxious, right? So unstable means you have high energy, stable means you have low energy. Just deal with the energy. So just try to see in which theta case dipole will have less and more energy. So energy or formula for dipole was what? Minus P cos theta. If theta is zero, energy is how much? If theta is zero, then energy is how much? Minus P. If theta equal to 180, energy is how much? Plus P. Which energy is more? Plus P. Unstable means theta 180. Stable means theta 0. This is all done. Only one thing is left here, but before that, I want you to do one question at least. This topic is too big actually. Chalo, so now we will do this thing. Okay, this is a very simple question. I am giving you 1 minute of time to do it, and after that, I will solve it, and you can do it as well. So do it fast. Do it fast as you can. I know everyone is exhausted. This 1.5 hours of lecture. But koi nahi, tomorrow we will be doing question. And because this was too much lengthy, I needed to explain things. So no worries, do it now. I hope you all must have read the question at least. So what the question is, electric field in a region is radially outward and at a point is given by E equal to how much? 250 R, where R is what? Position vector. Done. Calculate the charge contained in a sphere of radius 20 centimeter centered at the origin. ठीक है. Charge contained in a sphere निकालना है आपको, जिसका सेंटर कहाँ है? Calculate the charge contained in a sphere of radius 20 centimeter centered at the origin. Its center is at origin. And from origin, and from this position vector only, electric field is written as 250 R. Done. So you have to calculate the charge contained inside this configuration. Which formula you're going to use? अगेन चार्ज कंटेंट पूछा है, क्यू इनक्लोज पूछ रहा है, ठीक है, तो फ्लक्स का फॉर्मूला हम लोग यूज कर सकते हैं, है ना, कौन सा फॉर्मूला, गॉसेस लॉ, क्या, व्हाट यू विल बी यूजिंग, E dot ds, E dot ds equal to how much, q enclosed by epsilon. Done. So simply calculate E dot ds. Electric field is in the radial direction only, 250 r. Done. So electric field is like this, done. And how much is its value, 250 r. So for this surface point, at each point of the surface, electric field value will be how much? Electric field value will be 250 into r. Radius value is how much? 20 centimeter. So here you are going to write 250 into 20 centimeter means 0.2 meter. So electric field value is this. Now angle between E and ds is how much? 0 degree, because electric field is this. Normal to the surface is also this. So again cos 0, 1 ho gaya. ds will be how much? You have to calculate its area. Area will be how much? 4 pi r square. Done. So what you are going to write, question is very simple. 4 pi r square. Area likha maine. Area into electric field 250 into 0.2 will be equal to how much? Q enclosed by epsilon. So from here you can calculate Q enclosed by epsilon naught. Done. So these are the things. Correct answer will be 3 actually. I will be sharing more question for you to solve. Done. That you will be getting in your notes. Till then, आप लोग अपना ख्याल रखो. Take care of yourself. Stay fit and healthy. And on top of that, stay positive. Don't take tension. Whatever will happen for good. And whatever will not happen will also happen for good. Okay? So you don't have to worry. You have to just keep on working. That's all. Okay? Bye-bye. Tata. Take care. Let's meet tomorrow.